Today, we will learn how to calculate bending moment diagram. In order to do so, we need to have first a beam that we have there in blue color, and this particular beam has two reactions that we calculate with this load. The sum of the reactions, 25 plus 5, need to be 30, and this is the process that we did in the past. We also calculate the shear diagram with the part in 0, went up 25, nothing happens, go straight. After we go down 30, that means that from 25 positive, we arrive to -5, we write -5, nothing happens, and coincidence, we have 5 here, that means the beam closed. If the beam doesn't close, you have problems and you need to look if the reactions were correct. The fact that the reaction 25 and 5 go together and make 30 doesn't mean that the reactions are correct. I could have a mistake and have 24 here. After I don't calculate the moment in the other side, I just decided to tell that this is 30 minus 24, this is 6. And 24 plus 6 is 30. That doesn't mean that 24 is the good reaction. The reaction is 25. Well, be very careful about that. After you have your diagram, you can start doing your bending moment. And again, you just need a line that shows you what values are up to 0, positive, and what values are negative. Also, dot lines where the beam start, where the beam end, and because this is a very easy one, we only have another dot line that show the place where we have the only force that is 30. Reactions are on line with the end and start of the beam where we don't need additional points. There are two ways to do this. The first way is using the cutting the beam method. That is the one that used the book that I will not recommend because I think that is a lot of work. I will prefer the area method. However, for this exercise, I will explain you the cutting beam method. How is this cutting beam method? Well, first, you will forget that we calculate these areas because you don't need it. They are there, but you don't need it for this method. And what you will do is that you will cut the beam. You imagine that you are cutting the beam in many places. For example, I will cut the beam I will imagine that I will cut just before the beam starts here. Well, I cut the beam there and I don't have any force. Well, I move a little bit and I am just where 25 is. When I cut the beam in 25, what will be the load? Well, when we cut the beam, we are looking what happens in the side of the beam that is in the left. I mean, if I cut here, I only look these forces. I will not look what happens at the right. Why? Because I put together what is in the right and together what is in the left, I will always have as a final solution 0. The total force shear or the total bending will be 0. For example, if I cut the beam here, I look at the left and I have 25. I look at the right and I have 30 negative and 5. That is equal to 0. If I cut the beam here and I look at the left, I will have 25 and 30. That means 5. But at the right, I also have 5. One is positive, one is negative. -5 plus 5 is 0. Well, any place that you cut the beam, the summatory of shears and sum of bending moment will be 0. But instead to do that, you can cut the beam and look what happens in what side. Then you will know what is the shear in that place. If I cut the beam here, for example, near to 25, the shear will be what I have in the left, that is 25. If I move a little bit more, it's 25. And in fact, that is what my diagram is telling me. It's telling me that it's 25. If I move a little bit after 30, how much will be my shear? Let me clean this. I cut here. Well, what I have in the left is -30 plus 25. It will be -5. And in fact, look, it's -5 here. And it will be -5 everywhere where I cut. Well, the shear diagram is the plot of the forces that I have in the superior part and will tell me what is the shear in each place of the beam, like here, 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 here. I know that the sum is always 0, but the shear in a specific place is what you have at the left of that place. That is equal, by the way, of what you have at the right, because together they have a total of 0. If I look here, what is at the left, I have 5 negative. If I look what I have at the right, I have 5 positive. Well, that's why the shear can be calculating with this method that you cut the beam. Well, if we will do the same for the bending moment and we cut the beam just near 0 and it's 0. If we move a little bit more, will be 25 multiplied by a small distance. If I am very near to 25, that will tend to be 0. If I move a little bit more, 0.0000 something, it will be almost 0. But if I move more and I arrive to 0.1, 0.31, for example, I arrive here to 1, I will need to multiply 25 by 1. Well, 25 multiplied by 1 is 25. I will need to plot 25 here until in 1, the bending moment is 25. I got it. If I cut the beam just before 36 in 2, how much will be the moment? The moment will be what I have at the left, 25 multiplied by 2, because remember, shear is summatory of vertical forces. That's why here is 25. But moment is force multiplied by distance. 25 need to be multiplied by this distance. That is 2. 25 by 2 is 50. Well, I just write 25 by 2 and I plot here. The next moment will be what happens in 3. I cut my beam in 3, that is approximately here, and I look what happens. Let me clean and cut again. And what will happen is that I have 25 multiplied by 3 minus 30 multiplied by 1. And that is what I have here. 25 by 3, 75 minus 30 is 45. Next, I cut in 4. I cut in 5. I cut in 6. And I still have the same calculations to do. 25 by 4, 30 by 2. 25 by 5, 30 by 3. 25 by 6, 30 by 4. Why? Because every time I move 1 unit, and this distance is 6, for example, and this distance will be 2 numbers less, 4. And I need to do this for every one of these elements, and that is too much. That is too much work. Well, if I know that the bending is 0 here, and I know that the bending is 0 here, and I only have one place where I need to do the calculations, I just need to calculate how much is the moment in the point 2, and just put 2 lines together, and that's it. How much is the moment in point 2? Well, first method, I cut, and I say, just before 30, 25 multiplied by 2, that is 50. I could do the contrary. I could just tell 5 multiplied by 10, because now I look what is at the right, and it's also 50. Guys, I just go up in my scale. Sorry, I just write here 50, make a line, find that point, and that's it. I know that the other numbers will be an inclined line, because here is 25, it is 45, 40, 35, 30, 25, 20. Those are the plots line. Well, why to do all that job? I just need to learn that when I have a straight line here in the beam, I will have boxes. When I have boxes in the shear, I will have inclined lines over there, and that is all. But if instead to have one, we have several cuts, that will become a little bit more complicated. That is where I recommend this area method. Look what happens here. If I calculate the area of this rectangle, I will need to tell myself this is a rectangle where the base here is 2 units, and the side is 25. The area of that rectangle is 50. Got it? And if I cut the beam here, I am doing exactly the same. I am multiplying 25, that is this side, by 2, that is this distance. That is the shear just before, that is the moment just before 30. It's the same that calculating the area. And if I do the same here at the end, how much is the shear? Well, the area. The area will be 50, and this will be 10, that is 12 minus 2, multiplied by 5, that is also 50. Well, the moment in this point, just before 5, will be summatory of moments. Just before 5, 0.5 will be 5 disappear, 30 multiplied by the distance, negative, that is 300, 25 multiplied by the distance, that is 12, is also 300, is 0. Well, why to do all these calculations when we can just calculate one area? I calculate the area, I know that it's 50, I go inclined line because it's proportional, and after I need to close in 0, and yes, the area is 50, that is no mistake, I close in 0. And my diagram is ready. Let's look at the second one. For the second one, it's a little bit more complicated. We have two forces, and you already know how to calculate in step 1 and step 2, reaction 1 and reaction 2, and in step 3, this is step 3, and this is step 4, I'm sorry. You know how to calculate the shear diagram, and you know how to calculate now the moment diagram. What do you do? For the other method, you start in 0 always, finish in 0 always, and you cut the beam just before 21 is 0. In 21, you will see 0 for something small, very small, but if you cut in 2, will be 21.667 multiplied by 2. That is the same that calculate the area. Well, let's calculate the areas instead. It's easier. You will calculate the areas of all the geometrical figures that you have. The first is 21.67, that is this red line, multiplied by this distance, that is 2. That is 43. In many books, they will put lines there. I don't like to put the lines if I do it, but I like to make a box and put 43 in the box like this. I know that that is the area, 43 something with 3 decimals always. The second one area will be this triangle that I will put in green color. And you have here 1.67 multiplied by this distance, that is 4. 6 minus 2 is 4. Base multiplied by height, we have the area of a rectangle. And the last one will be 8.33, that is this side, multiplied by this distance. That is 6. And that will be 49.998. The truth that this is 50. That is the real area, but we lose some decimals here because it's 8.33333, many threes. And that will be 49.999999. That is 50. Well, it will not be exact many times because of the number of decimals, but we have the 3 areas. Something interesting is that the areas that are positive, 1 and 2, 43 and 6, 8 need to sum together 49 because the sum of forces is equal to 0. Well, let's draw the diagram. As you know, every time that we have a block, it's like we have a sandwich bread and we're dividing in tranches and each one have the same weight. That's why from 0 we go up with the same inclined line, exactly the same. Well, we start in 0 and this line is 43. We draw 43 in a scale and that is the number 43. And we put those numbers together. The next one is 6.68. This is positive, this is positive. I need to go up. I go up 6 units, is this line. Therefore, I arrive to 50. And I close my line here, draw my line. And I arrive to 50.002. Remember, decimals are tricky. The number should be 50, but it's a little bit more. Finally, in the last part, I have this area that is 49. Well, that area is exactly what I need to do. go down 49 and arrive almost to 0. It's not exactly 0, but it's okay. A small difference, it will be always there. Well, in few words, guys, if I cut the beam here to look how much is the moment, I am doing exactly the same. I am multiplying 21.667 by a distance. Imagine that this is in 8. Well, I will be having let me clean everything to do this. Let's do it easier. Let's cut here in 3. If I want to know how much the moment is in 3, look what I do for the method of the book. I multiply 21.667 by a distance that is 3. Well, that will be 21.667 by 3. Well, I will take this element here until 3, and I will multiply the 21 by 3, and that will be 60 something. It will be like a rectangle like that. You see? And after, I will have 20 multiplied by the distance of 1. Okay? This is positive. This one is negative, and that will be 40. I will be eliminating the 40, and I will arrive to the same area. Well, look, this is the rectangle of 21 multiplied by 2. When I multiply 21 by 3, I have this 21 by 3, and after I multiply 20 by 1, and that will be this area that we have here, 20 multiplied by the distance of 1, and I will take out to 21.63, I will take out this area. It's like sum of areas, it's exactly the same. 21.667 multiplied by 3 is an area of approximately 65 something. And we have 20 multiplied by 1, and that will make approximately 20. Well, when we put them together, it will be 45 something. That is the number that go here. The plot that I am doing. If I cut in 10, what areas I will have? The summatory of moments in 10 to the left will be 10 disappear. We have 20 multiplied by 4, and we have 21.67 multiplied by 6. Well, that will be 21 multiplied by 6. It will be all this area in yellow, and after we will have 20 multiplied by 4, and will be what I need to take out to get the rest of the area. One positive and the other negative. And that's it. Well, to make this easy, it's better to just calculate area. We have 43 minus this other area minus this other area minus plus this other area, and we arrive to 0. And we plot them. 43 here plus 6, we arrive to 50, minus almost 50, we arrive to almost 0. Maximum moment, 50.002. That in the truth that is 50. And that's it. Let's go to the next one. The next one is a little bit more complicated because we have a distributed force. And as you know, in a distributed force, when we have the shear diagram, we go up, nothing happens, we go straight. But after, because this is like a bread divided in small parts, we need to go little by little in an inclined line and close the diagram. What will happen with the shear wear? When we have a box with straight lines in the top, this became an inclined line. When we have an inclined line, that became a curve. And that's what we'll be doing now. Again, we can go into all method and tell ourselves the moment is 0 is 0, the moment is 1, is 20 multiplied by 1, we go down up 20, and this is the point. In 2 is 20 multiplied by 2, 40, in 3 is 60, in 4 is 80. After we go to the next one, in 5, for example, it will be 20 multiplied by 5 plus this element in the center, that is 10, multiplied by the distance, that is 0.5, because we are just calculating how much is this. And that will become complicated because the truth is that we have several forces that need to be multiplied by that distance, and every time will become a little bigger, a little bigger, a little bigger. Well, we have 80, and we go down a little bit more, and that is what happens here. We draw 80 as an inclined line, but after this element is this moment in this area, and we need to go up as a curve. We calculate the area of this triangle, and this triangle is a triangle that is exact. Well, this area here, this number and this number are the same. This is 2, this is 2. We multiply 20 by 2, 80 divided by 2. Let me go, if I did a mistake. This is 4, this is 2. Yes, we multiply 2 by 20, that is 80, and that is the area of the rectangle. But because we need a triangle, we divide by 2. And it's written here all the information that you need. The area of the rectangle is base by height divided by 2. Well, it will be 20. The next, by coincidence, is the same. It's the same because we start in 20 and we finish in 20. It's just dividing this into parts. Well, it will be 20. And the next area will be 80. Well, we'll just go from here. This is plus 80, going up 80. We plot this area that is 20, we go up to 100. We have 100, we have 20 again, but negative. Well, we go in a line that is inclined, and you arrive to 80, negative. And finally, you have 80 here. That means we go down more because this is negative, and we stop in 0. And after here, we'll continue in 0. There is no area where we finish in 0. And that is, there is something very interesting here. Look, I can make a curve like that, but also I can make a curve like that. One is growing and the other is not. Concave and convex. See, 1 or 2. Which one of the two curves is? Well, that is tricky, and I will show you a method that I think that works very well with the students. Look, as you know, this is like a bread, but this bread is a triangular one. Well, those tranches are very big. And if you imagine that this number 20, this number 80, this height can be infinite, well, those tranches can be infinite, can be enormous. Instead, those little pieces here are always very small, are almost 0. Well, because we are doing sum of areas, we go up 80, and now we have 20, we need to go up. The curve will grow very fast. I mean, growing fast means taking very big steps. And after, little by little, will become a little bit more flat until the moment that it's not growing anymore. In few words, here, the plotting go from 80 very fast to a number that is bigger. If this number was infinite, this will be a line that is vertical. It's going to infinite. You see? But here, the plotting is growing so small that it's almost a horizontal line. That's why we start with very inclined lines going up a lot, and after we almost don't grow anymore. That's the reason why this curve is a curve that is like this, concave. If was convex means that in the first moment, the tranches, it will be a triangle like this. The tranches are very small, it's like flat, and at the end, the tranches of this bread in my triangle are very vertical. Well, it will be a curve like that. If we had, in the case that we have these two triangles, the curve will be like this. but that is not the case. Well, for the next test, I will not pretend that you know how to do this kind of curves. I will not pretend that you know how to calculate the areas of triangles that are weird, because this is very easy. Well, your exercises will be easier, but you will have 1 week after where you can practice this more, and after we will have, that will be week number 5, and after in week number 6, we will review this material again, because this is a little bit complex, and I understand that probably the first time you will not get it. Well, we will start, I am explaining all the exercise in general because you will be curious, but we will later on work again with the most difficult. Well, let's do one that is a little bit more difficult. Look what happens here. We have a distributed force in the center and a force over there. Well, when we do our beams, it will not a big deal. We calculate our reactions and we go up 36, nothing happens. We go down 20, we arrive at 16 something, nothing happens. We have a distributed force of 10 kilonewtons, that will be 4, therefore this is 40. And we start going down from 16, 40 negative, that is 23. And we go down with an inclined line. After nothing happens, and we have a force of 23, and well, we go here 23, nothing happens, and we close the beam. The deal here is that different to the other one, where we have an element that you go 20, and you arrive to 20. In this case, it's different. In this case, we have here 16, and here we have 23. Well, the line is inclined in a way that is not 45 degrees. And this area of this small triangle will be different to the area of the big triangle. Well, that is what is complex in this particular element. It will not be difficult to find the areas of the other rectangles. Look, this rectangle is 76. Why? 36 multiplied by 2. Next one is 20. Why? Because we will have 16 multiplied by 2. This is a mistake, I apologize. Let me correct this here. Let me close this one here. Well, we already have that here, no? It's 33.334. I just copied this number wrong. 33.334. And for the next one, the last one is 23.33, that is this vertical line multiplied by 4, and it's 93.32. But we don't know the two triangles, triangle 3 and triangle 2. We don't know because we don't know how much are the distance. Before the distance was the same, but now the base of the triangle are different. I know that this base plus this base together is 4 units. I also know that this side plus this side is 16 minus 23, that is 40 units. 16 positive plus 23 all together, because you imagine that it's the same sign to come make this vector, you have 40. That obviously is this weight, 40. But we don't know how much are each one of the triangles. And for do that, we have a theorem that is called theorem of similar triangles. If you forgot this, look in internet what that means. And that means the following. If I have a triangle like this, I can divide this triangle in different parts, like for example, like this. And I have one triangle that is in red color. I have another triangle that is in yellow color. I have my original triangle in brown color, and they will have the same proportions. Why? Because they have the same inclination in the base, they have the same inclination, that is a vertical line in the side, and they will have the same inclination in the main cathete. You see? Well, that is a very good news, because having a good proportions is exactly that, making what I will do now. I will draw this big rectangle. It will be the blue one. Let me change color. I will draw the blue rectangle, that is this one. I draw that rectangle there. It's already here, but I will do it again. And this is the blue one. If I divide that with a vertical line, horizontal line, I have two. I have this one in yellow, and I have this one in red. Why the one in red? Because the one in red is the same that this red. I mean, it's a rectangle that I divide into parts. This and this are the same. Because that's, for that reason, are called similar triangles. They have the same elements. Well, in few words, the proportions are the same. If the triangle blue have a proportion that tell 40 in the side, okay? And have a base of 4, the yellow one that have in the side, that we already know the number, 16.67, will have a number very similar to 4 in proportions. In few words, look what happens here. If you make $40 when you work 4 hours, that means that if you make $20, you only work 2 hours. Well, if you make $16.667, how many hours you need to work? The same, you will tell 16.667, and you will make this rule of 3. You multiply by 4, okay? Because that is the proportion, and you divide by 40. And that will tell you the number of that base. Got it? We can look something very similar before, but we didn't need it. We did not need, but here in this particular, yes, in this particular element is the same. We know that was proportional, and because this side is 20, this side is 2. Well, you say for 20 as a side, I have a base of 2. If my new side is again 20, how much is here? 2 hours of work, $20. 2 hours of work, obviously $20. That means I will take 20, multiply by the numbers of hours that the other job offered, that is 2, and I will divide by the number of hours that I need in the other job, that is 20. And that will be the same. It will be equal to 2. Well, if you change the proportion and you say, I make $80 when I work 4 hours to make, for example, $10, how much I need to work. You say 10 multiplied by 4, 40, divided by 80 is 0.5. It's obvious. You are making here $20 per hour. If you need $10, you only work 0.5. And that is the multiplication that you do. The operation that you do, you multiply 10 by 4 and you divide by 80. Well, you will do always the same with the similar triangles. For example, you will make a triangle that is the big one. Why the big? Because it's the one that you know the numbers. And you calculate the proportions, and in this case is 40 by 4. If you want to calculate this triangle, it will be the same that having another triangle there, and you divide into parts. This is the small one, this is the big one. Okay, the big one has a side of 23.333. You don't know how much is the base, that is this one. Let's change the color for this one. This will be the big one. I will put in pink. And I want a red one. Well, what you do, you just tell yourself, in the original one, I have a base of 4 and a side of 40. Well, I start for the side that I know the side in both sides. I start by 40 here, equal to the number that I don't know in the other triangle, that is this distance. Well, 40 is equal to 4, what 23.333 whatever is equal to a number. Well, 23 point something multiplied by 4, use always the decimals, please, divide by 40, you multiply, you divide, and will tell you how much is this side. After you have this side, you multiply by the base, sorry, by the height that is 23, and you divide by 2 because you don't want the triangle, the rectangle, you want the triangle. Okay? And that's it. You have the areas, this one is 13, this happens to have 27, you put them together, and you know that they need to be equal to this weight, that is 40. I mean, this big one, that is 40. Because you have 16 plus 23, this side is 40. Okay? Well, you calculate the areas of this one and you start doing your diagram. Look, this is a box. I need to incline it. I always start in 0, finish in 0, and I write 76 here. I make a line. Let me take a bigger marker, a different color. A thicker marker. I start in 0. I write 70 and I make a straight line between them. Next, I have 33 as an area. From 76, I need to go 30 something up. And I go up and arrive to that number that is 106. Straight line. Next, I have a triangle. And this triangle is 13 and it's positive. Well, I need to go up 106 plus 13 and arrive to 120 something. I write there 120,557 and I need to make a line that is inclined. 2 options, convex or concave. Which one is? Big tranches mean vertical lines. Small tranches mean horizontal lines. Growing fast, not growing at all. Vertical, that became horizontal. This is the line grow fast and after doesn't grow. Pass through 0. Look, well, I need that line because pass to 0, there is a change of concavity. This is positive, this is negative. I need one additional line. I cannot go up again because this number is negative. The sum will be smaller. You are plotting areas. Positive area, you go up. Positive area, you go up. Positive area, you go up. Negative area, you go down. And well, as you know, it's an inclined line. Therefore, you need to go down in a way that is curve. Curve 1 or curve 2? Which one is? Small tranches mean horizontal, big tranches make vertical. That means the line cannot be like that. This is the contrary. Look, vertical lines, horizontal lines. It cannot be that. It needs to be this one. Finally, you arrive to 93. Why 93? Well, because 73 plus 33 is 93. Sorry, I did a mistake. 76 plus 33 is 106. Plus 13 is 120. Minus 27 is 93. Oh, coincidence, the same number that I need to arrive to 0. Straight inclined line, I arrive to 0. And I need to finish. The beam finish here. Well, the area here is 0, nothing happens. I go straight. And that is all. What is the conclusion in these two diagrams? The conclusion is very simple. Maximum shear is 36 because it's the higher number. 23 is negative, but that's not the problem. It's that 23 is a number that is not as big as 36. Maximum moment, 120. Look, something very interesting. This line is going smaller and here pass through 0. When the shear is 0, the moment is maximum. And that is the maximum moment, 120.557. Okay, I will go to the next one. The next one is easier. We have two forces, and what is complicated here is that because the forces are in different sides, you know that the shear diagram will be complicated. Not the shear, sorry, the calculation of the reactions will be a little bit complicated because some of them will be negative. If you calculate the moment here, to calculate, to eliminate this reaction and calculate that one, you know that 10 have a different sign of 20. That's why we have the figure of the little guy there. But the shear is very easy. You do the same. You go 11, nothing happens. You go down 20. Look, this vector, I will change the color. This black one have a length of 20, but it's going from 11 to minus 8. But the length is 20. Nothing happens. And after I had this yellow one that have a length of 18. I start in 8.33 and I need to arrive to 10 to have a vector of 18 long, that is this vector. Nothing happens. And after I have a last vector that is 10, well, I need to go, sorry, 10 in red, 10, I need to go down 10 and close. From 10, I arrive to 0. For the shear diagram is very easy. I calculate the areas because I understand that calculating the area is like cutting the beam and look what happens at the left. Look, this area is 46. Why? Because it's 11 multiplied by 4. Why? Because if I cut here, I need to multiply 11 something by this distance to calculate the moment where 20 is in the point 4. It's the center that. And when I do here, I will have this big one minus this small, and that will be that rectangle. It's like I have a big one here, okay? And I have this small there, and I put together and I arrive to that number. Well, I calculate this one, easy, 8.33 multiplied by 8, because this distance is 8 and this is 8.33. We have 66. Finally, 8.333 multiplied by 2, because this distance is 2, that is almost 20, because if I put many 3's there, it will be 20. Many number 3's. But I put the set number that is 19. Let's do the diagram. We start in 0 means that 46 is positive, I need to go up. I go up 46, make this line, and 46 is located there. Well, I make a straight line. This is yellow, this area, I make a straight line in yellow. Also straight, and I arrive to that number. Next area in brown is 66. Well, from 46, I need to go to 66. Well, I just write 46 plus 19. That is the distance that I move. The brown distance is 66. I go do here, go there, I arrive to this point. Well, I make a straight line because this is a box, the line is straight, and I arrive to minus 19 something. And that is just what I need to close the diagram. And that's it. Conclusion. The maximum shear is in the string in this area, and it's 11 point something. And the maximum moment is in this point, and is 46. That makes sense because look, when we look at this beam, this is the place where you have the maximum moment. How this beam will deflect? Well, it seems that this will push the beam up, this will push the beam down, this will be the pushing the beam up, and this will push the beam down. That brown line is like the deflected shape of the beam. We imagine that this push, the beam go up, this push down, the beam go down, etc., etc. But the maximum values are the ones that we have there. And we can do the same with the next exercise. You were supposed to do these calculations and understand how this curve is made. And we do the same. We calculate the area of this rectangle. We calculate the area of this rectangle. We calculate the area of this little triangle, and we put together with this. This will be the word that we need. We need another area of this little rectangle, another of this little rectangle. This area here will be one rectangle plus that one, and we put them together. Okay? Well, in few words, we'll cut the beam here because we have a force, and we calculate this area. We have a force that start, we cut the beam here, and we calculate now the yellow area. We have another force of 20 here. That means we need to calculate, we plot that, and we need to calculate this pink area. Here we have this, and that will be these two areas, 1 and 2 are separate because we change from positive to negative. Well, you need to calculate them separate. Okay, well, let's tell that one will be green, the other will be yellow. This is the green one, and the other is the yellow. Finally, we look what happens in the other side, and it's divided into parts. Let's call this blue, and it's this area. How you calculate this area? Well, you divide into parts. This is a rectangle, and this is a triangle. You have the numbers. 279 minus 79 is like 200. 200 multiplied by 4 divided by 2, and you have the area of this triangle. Plus this, and you put together, and you have this area. And finally, you have the little one that is there, and you just plot straight line against straight line, inclined line that is growing and going to sleep is smaller. The same happens here. Here is the contrary, it's very flat and became more inclined. Here is a straight line. Sorry, this is an inclined line because this is inclined. This is a curved line. The number is negative, and you close there. The same happens with this diagram. You calculate the areas and plot this diagram and this diagram. They are very similar between them. We will be reviewing this in 2 weeks. Well, this week you will be working and you will have a task. After you will have 1 week where you will look theory, but you can continue studying this because we will be doing more exercises in the week number 7. And this concludes